We now come to the third part of the course where we're going to talk about climate change. So first we have to understand climate and the greenhouse effect. Greenhouse effect is named for physical greenhouses, which are used to create nice growing environments for plants. And the way that works is you have a glass roof. Sunlight comes in through that transparent glass roof. It heats up the air and the plants, everything that's inside the greenhouse. And as warm, dense things, that heat then tries to radiate away. It can't radiate through the glass because the infrared radiation that is emitted is absorbed by glass, and there's a demonstration that illustrates that effect. And also, it can't lose the heat by convection. The air warms up and it expands, but it's got nowhere to go just because there's a physical roof on top of it. That's also why your car gets hot when it's left out in the sun. So nothing particularly fancy or surprising there. And quite honestly, there's nothing particularly fancy or surprising about how planetary greenhouse effect works. The difference is that instead of a physical trap of that energy, it is a spectral trap. It is a trap of the radiation. So how does a planet work in the very big picture energetically? Sunlight comes in, that we already know is where virtually all of the energy that's arriving at the surface of the planet is coming from. A very, very tiny amount is trickling out from the inside from radioactivity, causing internal heat. So we've got all this energy coming in from the sun. It's delivered primarily by visible light because that's where the sun is brightest, and that warms the planet. And we know that any warm object, law of nature, warm, opaque objects radiate energy. That's why the sun is radiating energy. It is a warm, opaque object, and it is radiating sunlight. The Earth is a less warm object, and so it radiates its light at a different wavelength than the sun. It radiates it in the infrared, which we can't see with our eyes, but if a planet is in energy balance, then the amount of energy coming in equals the amount of energy going out. Otherwise, you'd get an accumulation of energy in the planet if more energy was coming in than going out, and it would heat up and melt or evaporate. Or if you had less energy coming in than was going out, the planet would cool off and freeze. Nature likes to make things balance out. So you put a perturbation, turn up one valve to make an input bigger, then it'll take a little bit of time for nature to respond so that the output matches the input. But in equilibrium, the sunlight coming in has to be balanced by the infrared radiation leaving the planet. That's indicated in the previous, somewhat more artistic drawing, and in this schematic here. Sunlight energy is coming in, that's indicated by the orange straight lines, and then that warms the planet and it radiates its energy away in the infrared, that's indicated by the curvy red lines. And this looks like a messy physicsy sort of uh, slide, but we've got the diagram here just showing that Earth energy balance, sunlight in, infrared radiation out. And the important thing to take away from this slide is that we can calculate how much energy is emitted by the planet from this equation, and it depends on the temperature of the planet to the raised to the fourth power. The other A is how the surface area of the planet. E and sigma are constants that we don't need to worry about. The solar constant, the input of energy into the planet, is known. We know how bright the sun is, and we can measure that. So we know how much energy is coming in. This equation tells us how much energy is going out. It just depends on the temperature and these other factors that don't change. So if we balance those two things, if we say, here's how much sunlight is coming in and how much power is going out, if I try to balance those two things, remember that the average amount of energy coming in from the sun reaching the surface of the planet we said was about 240 watts per square meter after taking into account absorption at the top of the atmosphere and spreading that sunlight out over the entire 4 pi r squared surface of the Earth. If we set that equal to the output radiation given by that equation with sigma t to the fourth, we can just say, okay, well, how warm does the Earth need to be in order to be in energy balance? And the answer that we get is 0 degrees Fahrenheit as an average temperature for the Earth. Well, that's obviously much colder than what the average temperature for the Earth is. So what mistake did we make in doing this calculation? Well, the mistake that we made is that we forgot to include the effect of the atmosphere. And what the atmosphere does is it prevents some of that infrared radiation from getting out into space. And instead of leaving and going to space, that energy is absorbed by the planet, the atmosphere, and the surface. And so ultimately, the energy has to get out. In order to increase the energy output, what has to happen is the temperature of the planet has to increase. This equation here, P equals E sigma AT to the fourth, says if I want P to be bigger, I've got to increase the temperature. So the temperature increases so that the Earth can then be radiating more energy out because it's trapping some with that the effect of the atmosphere, the greenhouse gases in the atmosphere. And the way those greenhouse gases trap, we'll be talking about in this module, and you can see some of the demonstrations, but they are keeping some of those red squiggly lines that you see in the diagram from making it out into space, and instead are turning them back, pointing them back down to the Earth. So it's essentially like they're increasing the number of yellow lines going into the Earth, which then means a higher energy flow in. We need a higher energy flow out. To get a higher energy flow out, we need a higher temperature. So at the present time, the Earth is actually the beneficiary of a 33 Kelvin greenhouse effect. Without the Earth's atmosphere, the Earth would be much, much colder than it is, 33 Kelvin colder. So we owe our ability to survive in liquid water on the surface of the planet to the presence of a greenhouse effect. If there were no such thing as atmospheric greenhouse effect, we wouldn't be here. So it happens, and it's happening to a pretty robust effect on Earth. And as we'll see later, different planets have different amounts of that greenhouse effect.